Hello everyone, this is Professor Roman. Welcome to the 28th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to begin Chapter 5 of the accompanying book, The Principle of Inclusion, Exclusion. Up to now, much of what we have done has depended either directly or indirectly on two important counting principles: the multiplication rule, also known as the fundamental counting principle, and probably to a lesser extent the pigeonhole principle, still very powerful. In this chapter, we're going to look at a third principle, which is every bit as powerful as the two I just mentioned. It's called the principle of inclusion-exclusion. So to describe this principle, let me give you an example. Consider a group of 60 students, and we are told that 40 of the students are taking a math class and 30 of the students are taking a computer science class. The question is, can we tell how many students are taking at least one of the two classes? Well, the answer is no. We don't have enough information. It certainly can't be the sum, 40 plus 30, because that's 70 and there are only 60 students. It could be as few as 60 students if all of the 40 students that are, it could be as few as 40 students, because if all of the 30 students taking computer science are also taking math, then the answer would be 40. So it's somewhere between 40 and 60. The reason that we can't tell how many students are taking at least one class is because we don't know how many students are taking both classes. Okay? Now it's worth thinking about that until it's pretty obvious, because this is the heart of the principle of inclusion-exclusion. If we knew, for example, that 20 students are taking both classes, then in the sum, 40 plus 30 of the students that are taking math plus the students that are taking computer science, that's 70. We've overcounted the 20 students who are taking both classes, overcount by 1, because they're counted in both the 40 and the 30. So to correct that overcount, all we have to do is subtract 20. So, in this case, the number of students who are taking at least one class is 40 plus 30 minus the overcount of 20, and that's 50 students. So, speaking more generally, if we have two sets A and B, subsets of a universal set, the sum of the sizes of the two sets counts the elements in the union, A union B. Those are the elements that are either in A or B. It counts the elements that lie in both sets twice. Obviously, it counts them in the size of A and it counts them in the size of B. So we have to subtract the size of the intersection in order to get the size of the union. So this is the formula. The size of A union B is the size of A plus the size of B minus the size of A intersect B. And this is to correct the overcount in these first two terms. This is the principle of inclusion-exclusion for two sets. We include a number of elements in each individual set. We exclude the number in the intersection. So examples, in a certain group of 100 kittens, 50 are male and 25 are long-haired, and 10 are long-haired males. How many kittens are either male or long-haired? Now remember our discussion of disjunction. Or is inclusive or, so it could be both. Right? Male or long-haired could be a kitten that was both would qualify for that. So we just have to assemble our numbers for the principle of inclusion exclusion. The size of M, the set of male kittens, is 50. Long-haired kittens, we'll call those L. That size is 25. The size of the intersection is 10. This is the information we're given, so we can compute the size of the union to be 65. Now, the principle of inclusion-exclusion gives us a formula for the size of the union, A union B. These are the elements that lie in at least one of the two sets. Therefore, it also tells us the number of elements that are in neither set, because it's the rest of the elements in the universe. So officially, according to De Morgan's law, we're looking at finding the size of A complement intersect B complement. Those are the elements that are in both complements, which means they're in neither set. De Morgan's law tells us that this intersection is the complement of the union, and that will be the universe minus the union, the set minus. So the size of the intersection here is the size of U minus the size of the union. And that's worth putting in a corollary because it comes up a lot. The number of elements of U that are in neither one of the two sets is given by this formula. Okay. You really don't have to memorize this one if you have memorized this one, because you're just taking this and subtracting it from the size of the universe. In a certain math class consisting of 100 students, 70 students passed the midterm exam, 80 students passed the final exam, and 60 students passed both exams. How many students flunked both of them, did not pass either one? U is the universe of the set of all students in the class. Let's say M is the set of students that passed the midterm. F is the set of students that passed the final. These are the data on sizes. And so the number of students who did not pass either exam is this number here. It's 100 minus the quantity sum of 70 plus 80, then minus 60. So when you drop the parentheses, it's 100 minus 70 minus 80 plus 60, so that's 10. Here's a more mathematical problem. How many integers are there between 1 and 600 that are divisible by either 3 or 5? Well, we let I be the set of integers between 1 and 600. I sub 3 be the set of integers in I that are divisible by 3, and similarly for I5. So the answer to this question would be the size of the union, either divisible by 3 or by 5. and that's equal to this by the principle of inclusion-exclusion. The intersection is the set of integers that are divisible by both 3 and 5. But 3 and 5 are relatively prime, so those are precisely the integers that are divisible by 15. In order to be divisible by 3 and 5, they have to be divisible by 15, and conversely. How large are these sets, I3 and I5 and I15? Well, it might seem at first a little testy, but if you look at it the right way, it's quite easy. The integers that are divisible by 3 are the multiples of 3. So we could write those integers as 3 times 1, 3 times 2, 3 times 3, all the way up to 3 times 200, which is 600. Do something similar for I5. So I3 has size 200, I5 has size 120, I15 has size 40. And we have what we need to use the principle of inclusion-exclusion to get 280. So there are 280 integers between 1 and 600 that are either divisible by 3 or by 5. The second part of this question, how many integers are there between 1 and 600 that are divisible by neither 3 nor 5, is going to be the rest of the integers. So it's going to be the size of I minus 280, which is 600 minus 280, which is 320. The principle of inclusion-exclusion that we've done here is for 2 sets. This can fairly easily be extended to 3 sets, or in fact any number of sets. And that's what we're going to do next. So let's move on to the next section. And this is the principle of inclusion-exclusion, part 2, which is for 3 sets. And I broke this up into 3 parts. We did 2 sets, we're going to do 3 sets, then we're going to do the arbitrary case of any finite number of sets, positive, of course, because I wanted you to see the pattern developing here. And this next version for 3 sets will show you the complete pattern. So suppose we have 3 sets A, B, and C, and I've drawn a Venn diagram for those 3 sets, and I've numbered all of the individual regions in the Venn diagram. So region 1 consists of that part of A that is not in C and not in B. So it's just the white space here bordered by these lines, these curves. Region 6 consists of the elements of A that are also in C, but not in region 7, which is the intersection of all 3. So elements in A and C, but not in B, and so on. Now we're looking for a formula for the number of elements that are in at least one of the 3 sets. In other words, we want the size of the union of the 3 sets. Now we can reason, just as we did for the case of 2 sets, start with the sum of the sizes of all 3 sets and check for overcounts. Well, the elements that lie in regions 1, 2, and 3 are not overcounted. They're counted exactly once because they only contribute to one of these 3 terms. The elements that lie in 4, 5, and 6, however, are counted twice because they lie in exactly 2 of these 3 sets. And the elements in the center, region 7, are counted 3 times because they lie in A, B, and C. So we can first correct the overcount in regions 4, 5, and 6. Those elements are counted twice by subtracting the sizes of the 3 different intersections. A intersect B is all this stuff over here. It will correct the count in region 4. That's all I'm saying now. There are consequences of doing this. The consequences are that the elements in region 7, these are the ones we still have not counted properly, are now not counted at all because they're counted 1, 2, 3, -1, -2, -3. They're counted 0 times. So we correct that count by adding the size of the intersection of all 3. Okay? If you grasp this argument, you understand the principle of inclusion-exclusion. So here's the formula, and here is the formula, the corresponding formula for the size of the intersection of the complements of the 3 sets. It's the size of the universe minus all this stuff in the first part. And now you should see a definite pattern. First, add the sizes of each set right here. Then subtract the sizes of the intersection of each pair of sets. Then add the size of the intersection of each triple of sets. And there's only one because there's only 3 sets. This is the pattern for the general formula, which we'll talk about after we look at some examples for 3 sets. So suppose that in a group of 100 students, 50 are taking math, 40 are taking computer science, 35 are taking chemistry. If we want to know how many students are taking at least one of these classes, we have to gather together several more pieces of data. We have to know the sizes of the intersection of pairs, math and computer science, or math and chemistry, computer science or chemistry. Then we also have to know the number of people, students, that are taking all 3. So this is all the data here. Without this information, you can't answer the question. From there, it's a matter of just plugging into the formulas. These are the sizes of the various sets here, and this is the formula. So there are 97 students taking at least one of the 3 subjects. Okay. One more example from real life, you might say. In a group of 200 people, so this is a survey that maybe you've been hired by a company to do some marketing. You call 200 people. 100 like Coke, 149 like Pepsi, 83 like 7-Up. 80. So when you made the call, you would ask, which of these 3 soft drinks do you like? You gather this data. 80 like both Coke and Pepsi. 66 like both Coke and 7-Up, 45 like Pepsi and 7-Up, and 12 like all three. How many people don't like any of these drinks? That would be me. I don't drink soft drinks. And anyway, so this is, you set up these sets, Coke, Pepsi, and 7-Up, gather the sizes of the various intersections, and apply the formula. 47 people are like me. They don't care for soft drinks. I don't mind 7-Up so much, but it's kind of sweet. Okay, back to mathematics. One of the most important applications of the principle of inclusion-exclusion is to counting multisets with upper and lower bounds on their multiplicities. I'm going to mark this here and go back to a table. Well, actually, I don't need the table. I can just do the distinguishable boxes, no box empty. Look at this formula. You have this term minus this term plus this term and so on. That should remind you of the principle of inclusion-exclusion. And that's exactly where this comes from. So, let's look at an example. How many multisets of size 13 are there? Taken from a set of size 3 with these multiplicities. So we're now doing just upper bounds on the multiplicities. So let U be the universe, the set of all multisets of size 13 taken from S. Let A be the elements of the universe in which A1 appears at least 5 times. So I have sort of turned this around. I don't want the number of elements that have appeared at most 4 times. You could do it that way too, but this is a little simpler. The number of elements in which A1 appears at least 5 times. So this does not hold. Similarly for B and for C. Greater than or equal to 6, greater than or equal to 7. The answer to the problem then is the size of the intersection of the complements, because these are conjunctions. We need all 3 of these to happen. Okay? We need a complement to happen, and we need B complement to happen, and C complement to happen. And that's what this intersection is. So we do the usual gathering of data, the size of the universe, all multisets of size 13 taken from a set of size 3 is 3 multi-choose 13. And the formula, you add these 2 and subtract 1 and copy the bottom number over. Binomial 15 choose 13, which is 15 choose 2, and 105. Size of A. Set of all multisets of size 13 in which A1 appears at least 5 times. So that's now a lower bound. And so we do our lower boundary translation, subtract 5. Same thing for the size of B and the size of C. The intersection A intersect B is the set of all multisets of size 13 taken from S in which A1 has to appear at least 5 times and A2 has to appear at least 6 times. So we have two lower bounds, 5 and 6. Subtract the sum of the lower bounds, subtract 11, comes out to be 6. Same thing with the other two intersections. Finally, we need the intersection of all three. Number of multisets of size 13 taken from S in which A1 appears at least 5 times, A2 at least 6 times, A3 at least 7 times. Well, 5 plus 6 plus 7 is 18, which is more than 13. This cannot happen. So this intersection is empty. Applying the formula, this is arithmetic now, 6. There are 6 multisets that satisfy these upper bounds. One more example. Now we have both upper and lower bounds. So this is the multisets of size 25 taken from a set of size 3 with these bounds on multiplicities. The first step is to eliminate the lower bounds by doing lower bound translation. Okay. And so the answer to this will be the same as the number of multisets of size 25 minus the sum of the lower bounds, 13, taken from S, with these three upper bounds. Okay. Well, this reduces to a problem identical to this, except I've got different numbers here for the upper bounds. So I'll let you work through that. And what the answer is 18. Okay. We can also use the principle of inclusion-exclusion to count numbers of integral solutions. If you remember, that's just a different language for the same thing as multisets. And so I'll let you read this example for yourself. Well, okay, I think that will do it for this video. And next video, we'll talk about the full principle of inclusion-exclusion and its consequences. Thanks for watching, and I hope to see you in the next video.